Welcome back, everyone. I made a few updates since the first episode. You can see I added an icon to the project. I also got a GitHub set up for us, and so here it is. Currently, there's only the episode 1 branch, as you can see, and each branch is going to contain the code that was made during that episode. And so if you wanted to pick up on this episode and skip over episode 1, you could just download the episode 1 branch. Or if you wanted to jump on episode 5, you need to download the code from episode 4, and so on and so forth. And then the main will just always be the latest. So whatever is the most recent update, as you can see, it's been 5 days since I've touched this. But that'll be changing today when we write some code. And so as you can see, the icon actually isn't in the repository. I'll be adding it with the episode 2 code. So if you'd like to download this for your project, you can just download from the episode 2 code, and you can just take that if that's all you want. As you can see, I have this in the project, and in the project settings, I have icon set to that file right there. And so when we run it, you can see that there's the very small icon there, and down in my bar here, you can see the icon there. Now, I just made a very generic, very quick icon for this YouTube tutorial series. You can use any SVG or PNG file you want, so feel free to pick something that feels more you. And if you have your project set up properly, when you export, this will still be the file for the icon. If you have the right libraries set up for your exports, you can also have it be the icon of the executable, but I don't have those set up at the moment. At a later date, I can make an episode showing how to get that set up. So first, we're going to talk about some of the stuff on the Godot side of things, and later we're going to jump into C#. I did make an episode, a one-off episode, that should be live now, covering just the absolute basics of C#, and we'll be running into some things as well into this episode. So Godot handles things in a scene architecture. There's scenes and nodes. And so if you did the homework from the last episode, you must have found some nodes that look interesting. If you were an overachiever, you might have even looked them up to see what they did. If you did that, you probably found the Godot documentation, which is the ultimate resource for learning what nodes do and how to properly use them in your project. So these are the Godot docs. They are the best thing ever. Everything you could ever want to know is in here. You can search here for anything you want. You can go to the very bottom and you can choose where you want to be. For example, we're using 3.5, so we want to be sure we're on the 3.5 branch of the docs. That'll be sure to have all the extra things like the navigation server. And so it'll show you all the information you could need about the navigation server, which is the new way to get navigation for agents in 3.5. And so we might be touching this later if we choose to extend the series. I don't currently have plans to cover things like the navigation server and NPCs in the currently planned 16 episodes. If there's enough people following, I could definitely continue the episodes and go on to make the series longer. I would love to do that, and I'd love to see what everyone is interested in covering, because there's so much more to making games than just what I'm going to cover. But this series specifically is going to focus on the first-person controller and making a really good one that can be dynamically changed however you like it. Now, to explain what the point of nodes are, we need to explain some core concepts of the Godot engine. If you're familiar with Unity, Godot packages everything into nested prefabs. If that doesn't help, I can explain it this way. Each node does one thing. Sometimes that one thing is as simple as emitting a raycast or being a camera. The nodes are organized into a tree structure, which means that some nodes can be attached to other nodes, and it creates a structure where there is one node at the very top, and many nodes connect downwards to form branches. The single node at the top is called the root, and groups of nodes that connect down are called branches. And on an individual basis, a node that is above the current node is called the parent, and the node below is called the child. That means that every child has one parent, but each parent can have many children. Sometimes, to better organize the tree of nodes, we can use a placeholder node, which means that their function is really just to exist and take up space. Each tree of nodes is called a scene tree. They can then be saved to a file called a scene file. Generally, they're saved as a TSCN or an SCN file, where the TSCN is a text-based format and SCN is a binary format. Generally, you prefer the TSCN version because it's very easy to manage, and the overall file size difference is negligible. It also works a lot better because version control systems can recognize when a single line was changed versus the entire binary file of an SCN file. And so when you're making a change, it only has to push one line of text as opposed to the complete size of the scene file, which if you have a lot of embedded resources can get kind of big. What's incredibly powerful about scenes is that they are fundamentally just a tree of nodes, which you can add to another scene tree. This is called instancing because it makes a copy of the scene tree without removing the original file. This means we could make one scene file for each type of pickup item, and then make hundreds of instances across the game world. Each would behave individually, unless you script them to recognize the other instances. On top of that, when you're running the game, you provide a main scene. This is literally any scene file. On top of that, if you're running the game, you provide a main scene. This can literally be any scene file that gets loaded into Godot's base scene tree as an instance. This is the power of Godot. You can run any scene as a temporary main scene through the debug run option. You can layer complexity using more and more of these scene instances, and separate out coherent logic by grouping nodes into individual scene files. Then, adding functionality to one structure is as simple as instancing a scene that you've already designed. When I first moved from Unity over to Godot back in 2020, this was what really opened my mind to the possibilities of Godot. Unity demands that each scene is a separate structure from the individual game objects. The game objects themselves are given functionality by adding components. This is called design by composition, and it's one of the main pillars of good object-oriented design, as applicable to any software development when working in an object-oriented environment. In Godot, it should be said, is object-oriented primarily. You can use the object-oriented structures to develop a data-oriented system if you like, and I highly recommend doing this for some systems if you are an advanced user. But if you're following along this tutorial, you likely aren't that advanced yet. I'm going to focus on the object-oriented design for this series, with concepts like solid being integral to how we learn about things. Okay, I'm gonna put you down, kitty. I'm gonna see you later. Bye-bye. Now that we've had a look at how Godot handles nodes and scenes, we should start making our player scene. We'll start by making a new scene with a root node of kinematic body. So we click on the plus here to add a new scene. We want to hit not 3D scene, but other node. And then we can search for kinematic. You want the red one here, not kinematic body 2D. Click on that. And so what this means is that the basic functionality of this scene tree will be a kinematic body, which is physically simulated, but it doesn't automatically apply forces. So we get to define that ourselves. Now, an alternative would be to use a rigid body, which is physically simulated and exists in the 3D physics space. However, with a rigid body, you have to contend with all the other forces that are applied to it, and so you get less control, and it's a little more difficult to work with than using a kinematic body. And so that's what we'll work with here. Another element to choose is choosing what kind of style the player's body should have. For example, if there is no graphics on the player, there will be no shadow to cast, the player might not see anything. Sometimes a first-person character is just a pair of arms in 3D space, and that's all they need to be, because that's all the camera can see. But something I like to do is I like to add a mesh instance, and I like to give it a capsule. And so we can change in the transform, we can change the rotation by 90 degrees on the x-axis, and that'll make it vertical. And so now, because it has at least just a simple graphical representation, it'll cast a shadow. Now, we also need a good collider. That tells Godot what the shape of the physical object will be. Not the mesh instance, but a collision shape. So we can add that here. You want the shape, not the polygon. The collision shape, we can choose a capsule as well. And as you can see, again, it's on the side, so we have to go to Transform, X Rotation, and add 90. And so now it should line up perfectly with our capsule. If you want to change the shape of the capsule, you can go into the mesh and change the radius or the height. And whatever changes you make here, make sure to do it for the collision shape as well. And that's the basic structure of the character. But now we're probably going to want a way to look out. So we're going to make something that I call a camera rig. Basically, if you rotate one node many times in different directions, it can get pretty difficult to animate. And so the animation will end up overriding the rotations that you applied in code. So I like to add a chain of spatial nodes to help us apply rotations and animations in a fluid way. So first, we're just going to add a spatial. We're going to call it camera rig. You can double click on anything to rename it. We want to call this character controller. Now on the camera rig, we're going to add another spatial. And we're going to call it the Y rotation. Then we're going to add a camera. And we'll just call it camera. And so the idea here is the camera rig is the root of this branch. And we'll use the camera rig to animate things. And we'll use Y rotation to rotate on the Y axis. And camera can rotate on the X axis. And so that'll give a full range of motion from the Y rotation and the camera. And then the camera rig can be animated for things like camera shake. Generally, you don't need to worry about Z rotation. It generally looks bad when used. I can tell that from experience. You may have a case where you do want Z rotation or to separate the X rotation out from the camera. And in that case, you can add more spatials in between. Now, we're going to want to take this and move it to somewhere near the top, because right now it's in the middle. You can click on any of the little dots in this gizmo up here, and that'll snap to an orthographic position, an orthographic projection of that axis. And so now we can move this up, and you can see that it's snapping. If you don't want snapping, you can turn it off by clicking this, or the shortcut is Y. And so now you can see the camera is poking out here. Generally, you only want to move it on the Y-axis, which is green. And so you can see the camera's shape right here. And that'll be sticking out a little bit enough so that the capsule doesn't show. Now, we need to save this scene. And I want to talk about a really helpful approach to organizing your code and your game files. Most tutorials, if you follow them, the files will get saved any old place because it's just a throwaway project. But if you really want to follow along and work and expand upon a project, it's really good to follow organization principles early on so you don't have to reorganize everything later. Sometimes when you're moving files, references can get lost and then your whole system breaks and you have to spend hours debugging it. And so if we follow good organization approaches now, we can prevent that later on. Now, the approach that I prefer and I highly recommend to anyone developing games is the module approach. The idea is that we make individual chunks of code that we can call a module. And each module is for one thing. And in that module, we give it a folder. And in that folder, we have everything for that module. All the scene files, all the scripts, all of the assets, everything it needs to work so that it's self-contained. The power of the module approach is that Solid really encourages keeping code that doesn't depend on each other separated. The added bonus for us as developers is properly developed modules can be removed from their original project and reused in future projects. That means that a module we make, like this character controller, should be able to be drag and dropped right into a new project and work without a hitch. This approach also allows for a fun snowball effect, where as you work on projects big or small, you can carry over the individual modules, improve and expand on them if necessary, and then carry them forwards again. And you'll develop an ever-growing library of modules that you can draw on. I really like to stress test the usefulness of my modules with game jams, but some jams might not allow pre-existing code, so make sure to check with the jam rules if you want to do this. Now, let's save it into a character controller module. So I like to create a folder for all the modules, and then we're going to call it character controller. And I like to use kebab case for the module names, which means that the words are lowercase and you put a hyphen between each word. So we have character controller, and we'll save the scene here. And because hello world and the hello world script are not part of any modules, they were just to make sure everything works, I'm actually going to delete them. So we'll delete, and we will delete. And so that'll clean the root of our resources folder. So in our modules, character controller, we have our character controller scene, and we can close this out and just hit don't save, and it gets fully deleted. Now we're going to want to get our very first real C# script going. And so you can add the script just like last time. It's automatically called character controller because that's what our node is named. And you can see it's already putting it in the same folder as we save the scene, which is exactly what we want. And so I played around with Visual Studio Code a little bit to show you how valuable it is to have a good readable font, because this font is very pretty, but it's very hard to read. It takes a second to understand each word. And when you're programming, you want to be able to read it as soon as possible. So what I'm going to do is do Control comma. And if you search in the settings for font family, you can find editor font family. Now I'm going to remove that font, and whatever is the first one will be used. And if it can't find that, it'll move to the next one and the next one. In the last episode, my font was Ubuntu Mono, but I changed it to add Noto Sans Mono, which these fonts have to be installed on your system to be used. But now that we have that and we can save, it should be much easier to read and look more like the code that you're used to reading. There's a few common functions in Godot, and if you're familiar with Unity, these might look kind of similar. If you're completely new to programming in general, my computer science theory video for the core concepts of programming in C# is live on my channel, and you can check that out quick. I think it's only 5 minutes. And I highly recommend watching it before coming back to this segment, because I won't be explaining everything about the code. Now, Godot has a few core functions. The first one is called the ready function. It's called when the node enters the scene tree for the first time. Specifically, it waits until all of the children nodes of this node have called their ready function. So we can guarantee that any child nodes already are ready and have done whatever setup they need for themselves. You can think of it as an initialization or a constructor, but it's a little different, and there is a separate initialization option if you prefer. Generally, you want all of your initialization in the ready function. And most internal functions, they have an underscore as a prefix. And that is to denote that it is an internal script. This is a carryover from GDScript because GDScript does not have access modifiers. And so you can't set a function to private in GDScript like you can in C#. You also have to call override because it's an inherited node from the node class, as you can see. There's also the process node, which is called every frame, and delta is the elapsed time since the previous frame. And they also have some examples for initializing some member variables here. We're going to delete these because we don't need them. Now, process is called every frame after every frame is rendered. And there's another function that we can use that's also very helpful, called physics process. And we don't need to call the Bates version of these. Otherwise the logic is handled internally. These are only for our purposes. And so physics process is similar to process, but it's called at every physics step, which is a fixed rate, usually 60 steps per second. And the delta will be assigned to whatever the step rate is. Another really helpful thing that Godot adds, and you can see we have using Godot because it's all in the Godot namespace, is an attribute called export. And what that does is it's applied to any member variables to make them show up in the editor. And so we'll just have a public float speed. Let's have the default value be 2.0f. And so now if we save this, go back to Godot, click build, and click off, click back on, you can see we have our speed property and the default value, and we can change it here. And if you click the undo button, it resets to whatever the value is that you set in here. And so the code defines the default value, and you tell it export to give it a value. There's also some parameters you can give. For example, you can have property hint, range, and then you use a hint string. And so for range, it's 3 values. You have the minimum, then the maximum, and then the step value. So I'm going to say I want 0.1 as the minimum, comma, give it 999.0, comma, and then I'll use a 0.1 step size, just to make things easy. The step size is optional, but it can help depending on how granular of control you want to give for that property. So we can save and build, and you can see because we gave it a range, now there's a slider to change it. And you can see it's very, very fast because the maximum is 999. So if you know that you don't want to go over, let's say 10, then you can have the slider be a lot easier to handle. So I'm going to set this to a maximum of 10. And the slightly frustrating thing about C# is you do have to build every time you want changes. And so it's helpful to do a lot of coding and then a lot of editor work and separate those two tasks out as much as you can. But now you can see the maximum is 10. When we slide slowly, you can see that it changes a lot less. And so it's a lot easier to control and choose where you want to be. Because this is a character controller, we want access to input. And there's a singleton called input. It is action pressed. And it even, if you have it set up properly, you'll get some recommendations, such as UI accept, which is an action command. And this returns a Boolean, so we can put it in an if statement. Say gd.print. We'll say UI accept. Save that, and we can run it, because running will build automatically. We'll select current. And now if you press the enter key, it'll do the UI accept. And notice that we're only checking in the code if it is currently pressed in the process step. So every single frame it's checking, which is why it spits out a lot of them each time I press it just once. So now we can stop that. Optionally, you can change it to is action just pressed, which checks if it was just pressed once, and once it's been activated, it doesn't happen again. So if we run that, you can see it only prints out UI accept once for each time I press. Even if I hold it down for a while, it only prints one. Now, you can make your own input actions in the project settings and input map. And so each of these is given a name, and then you can have several bindings that tell it what inputs are associated with that. So you can see UI accept has enter, keypad enter, which is for the numpad, space, and then device 0 would be the first gamepad that is currently connected to the computer, and it has some helpful information. So it has the PlayStation Cross, or the Xbox A, or Nintendo B. And so that tells you which button on the controller it's looking for. So specifically, you can see that it's the east button, if you think of it as a compass. And so all of these are the default input actions. And most of them are for UI. They're used by the UI nodes in Godot. So if you change these, you can actually add inputs that control certain things or remove them if you like. And you can edit them with the edit button or delete them with the trash can icon. But right now we want to add some of our own. So we're going to add a few for movement. This episode we're making an axis aligned first person controller. And so we want to be able to move forward. We'll be able to move back, move left, and move right. Now, right now, they don't have any bindings, so they'll never be triggered. But you can use the plus icon here to add an event. Now, you could add a physical key, or a regular key, or a joy button, or a joy axis, or a mouse button. The physical key and the key are slightly different. When you use key, it checks against a scan code. So if you have it for the W key, wherever the W key is on the keyboard, it'll check for that input. If you use physical key, it'll translate the physical position of the key on the keyboard to wherever the scan code would be for that physical position. And so I use a QWERTY keyboard, so WASD is a comfortable movement binding for me. But if you have a different keyboard layout, it might not be as comfortable to use. And so I recommend using physical key when you want that kind of effect. Because that way, for me, moving forward is W. But for someone else, it might have a different binding. And this helps you support other keyboard layouts without really any work. And so I'm going to add physical keys. An S. I'm going to move left. With A. Move right. With D. And so that's all we have to do right now. We could also add a joy axis if you want to have a controller. And so you can see that there's left stick right, up, down, and then right stick. There's some dead space, and then there's some L2 and R2. Because the L2 and R2 can be considered to be an axis. On some controllers, they're actually a button, but it depends on the controller itself. Generally, Godot is going to assume you're using an Xbox controller, a PlayStation controller, specifically DualShock, or the latest Nintendo Switch controller. Other controllers are supported. I've actually used a USB N64 controller before, but you're going to have to set up the bindings very carefully for those. And it's almost easier to have a key binding settings menu to get those kinds of controllers set up. So for now, I'm just going to add these because I'm only working on keyboard right now. Later we can add game controller support, but right now we're just going to use that. So now you can see there were some changes, so we'll save that real quick. And so now when we go into our code, and if we say if input.is action just press, you can see we already have the inputs we want. So let's say move forward real quick. And we'll add a gd.print. And note I'm using just press because I want to check but when we're actually running, you just want to press. All right, so we'll go back and we'll run. So you can see when I press the W key on my keyboard, it'll move forwards. And these settings are stored in the Godot project file, which isn't visible in this file system, but if you're downloading it from the repo, it'll have all of these settings baked into it. So if you're downloading from this episode or from an episode later, the mappings will already be set up for you. Now that that's done, there's some helpful functions that Input has that were recently added called input.get vector. And what that does is we can give it the inputs for -x, +x, -y, and +y, as well as a dead zone if we like, which is really helpful if you're using a gamepad and you want to give a dead zone to the gamepad. And it'll return a 2D vector for the direction based on the 4 directional inputs. And so for -x, we're going to want to move left. +x, we're going to move right. -y, we're going to move backwards, which I just wrote as move back, and we're going to move forward. Now, autocomplete doesn't really work on getVector, but we can double check that these are the same names by going back into the input mappings. You can even double click and then copy it if you want. Those should all be the same. And so what this will do is give us a vector 2. And so we'll just say var input equals. Okay. We can delete all that. Now, the input is our direction, but we need to move. And it's helpful to have your movement be frame rate independent. And so what we want to do is actually move in the physics process when everything else would be moving. And so to make that easy, what we're going to do is we're going to have a private vector 3 velocity. We're going to make it to be vector 3.0. And so what we want to do is for our x velocity, so velocity.x is equal to input.x times speed, and velocity.z is equal to input.y speed. These two are different because the y-axis of the input vector is the forwards and backwards movement, which in 3D space is actually the z-axis. The y-axis is for up and down. And so you got to make sure these two are different. And we're multiplying by speed so that we can move faster. So right now it's multiplying by 2, because by default the maximum will be 1. Now, in the physics process, we can call move and slide when it loads. And you can see there's move and collide, move and slide with snap. We want move and slide. And so first it wants the velocity. It wants the up direction, which we're going to give it vector 3.up, because we're using a standard 3D position. Stop on slope, I want it to stop on slopes. Max slides will use the default. And the max floor angle, we can use math.deg2rad, and whatever maximum step is. I would like a 45-degree angle to be the highest slope that we can stop on. We can close that out. And so what that'll do, and you can see the description here, it moves it along a vector. And so if we save, now we go in here, we can run, and theoretically it's moving. But the problem is we can't see that because the player is living in a void. So what we're going to want is to make a 3D scene It's got a spatial. We're going to call it test level. Right? We're going to save it into modules. Go into modules, make one called levels. Okay, and we'll save test level. Now, we're also going to take test level and make that our main scene. We're going to add some nodes called CSG box. And these are really good for building out a level, but they're not very good for the finished product because they run very slow. And so they're really fun for testing out a level design if you want, but I do not recommend using them in the final product. Now you can see we have snapping on by default, which is either 0 or 2. So we can turn snapping off, or we can go into transform and configure the snapping, which we can choose what the snap value is. So it's 1 unit or 1 meter if you're thinking that way, 15 degrees, and 10% for scaling. I want a 0.1 meter, which would be 10 centimeters. And as you can see, we have a lot more granular option. And so we're just going to make this. You can use the scroll wheel to zoom in and out, middle click to orbit, and you can left click on these handles to move them out. Now, I'm going to add another CSG box. And what we're going to do is we're going to do the same thing. I'm going to move it up a little bit. And so you can see in the CSG shape side, it has operation union. Now, what this is the CSG objects use a Boolean operator, and so union will combine with the previous. Now, we can add another CSG box, and I'm going to actually Control D to duplicate and do that. And so now this is another one that's the exact same. We'll make it just a little bit smaller. Move it up just a bit. And then we're going to change this one to subtraction, which means it deletes space. And so now you can see we have a little world with space and objects. Now I'm just going to add another CSG cylinder here. Move it over here, make that tall. And what we can do here is we can click on the Y-axis, which if you hold Shift and middle click, you can pan around. And from here we can Control D to duplicate and then move. So what we're going to do is we're going to add some of these pillars around. And what that's going to do for us is it'll help us see the translation as we're moving around and give a little bit of scenery to help us look at something. Let's save that. Now if you want, you notice how we're still orbiting around roughly the center. You can press F to snap to the one you're currently selecting. And with the CSG objects, it's always the center that you focus on. Now, we're going to add into here, so we can click and drag the character controller, or we can do instance child scene, which will give us all of the scenes available. If you have a larger project, you might want to search for something, but generally, right now, we can match with the character controller, move that up a bit. It's a very large controller for the level we made, but that's okay. And so now, this is the main scene, so we could just press play. And we can see. And we move. And I can see that I got, when I press W, I move that way. And when I press S, I move forwards. And you can also see that we can clip right through this object because it doesn't have any collision. And also we don't fall when we move outside of it. That's because this is a kinematic controller, and so no physical simulation is applied to the object, but it'll interact with physical objects as any physics object would. So we can push things, but things can't push us, which is good and bad depending on the type of game you're making. So first, we're going to switch the forwards and backwards axes. The reason this is because we want forwards to be positive, but the camera by default is going to face the negative z axis. And so the negative of forwards is going to be backwards. And so we could go into the code and change these. Or we could set the z velocity to be the negative of input.y. This will achieve the same result and still allow us to conceptualize forwards as positive and backwards as negative, which is my preference overall because it feels more intuitive than negative being forwards. And so now that we've done that, we can go in here. And if we press backwards, it goes backwards, forwards goes forwards, and all that. Now, when we press the button, we're instantly moving at max speed, which is really snappy, but sometimes it's helpful to retain a little bit of the inertia. And we can simulate that using linear interpolation. So we're going to stop this. We're going to go back into the code. And so what we can do is instead of assigning it directly to the velocity, what we're going to do is we're going to do var target velocity equals new vector 3. And we're going to replace these with target velocity, semicolon at the end. And now velocity will be equal to velocity dot linear interpolate. That's a function available on all of the vectors. And so we tell it what we want as the target, which is our target velocity. And then the weight. This is how fast we want to interpolate towards this. And so in terms of physical simulation, you can think of this as the acceleration value, just how fast we reach the velocity. And so I'm going to put something called like 0.8. And because it's a time-based system, we need to multiply by delta. And so it'll interpolate every single frame, and the velocity will update accordingly, and we'll still move by the same velocity. So we'll save that, go back and try running. So as you see, it takes a second to start moving, and it takes a second to stop moving. And so this can make a little bit of a floaty feeling character controller. You want to be a little bit sparse with this. Another option you can do is you can have an acceleration value acceleration. Let's see, yeah. Stopping acceleration. She gets 0.99 f. And so what we can say is if target velocity dot length, and because of how length is calculated, we can use length squared instead, and that'll run just a little bit faster than the regular length calculation, which is good because we're doing this every frame. Less than or equal to 0.1 f. And so if that's the case, it's effectively 0. It could be a very, very small number, or it could be 0. We do less than or equal to just in case to cover that. And so we need var before I get acceleration, is going to be equal to acceleration. But now, we don't actually need this block if we don't want it. We can set target acceleration to our stopping acceleration. And I personally like to use snake case when it's a variable inside of a method, and camel case for member variables of the class. It's just a little helpful thing to separate information and help you understand what is where. So now, instead of a hard-coded 0.8, we can use our target acceleration. And so what this means is normally it'll be 0.8. But if we have an input vector that's less than 0, which means that either none of the inputs are being pressed, or if it's on a gamepad controller, the amount that it's moving, it's very, very small. And so it might just be noise from the controller. What we can do is save that and run it. And now it does take a moment to start, but it stops a little bit faster. And we can even change this. So because we're multiplying by delta, the acceleration is the number of seconds it takes to ramp up. So let's say we want to get to max speed in seconds divided by 5, and the stopping acceleration will make it 10.0. And so what this is we want it to happen in 1.5 seconds. So we need the inverse of it, which is 1.0 divided by it. And so if we wanted to have a stopping rate of 0.1 seconds, you have 1.0 divided by 1, which is going to be equal to 10. Okay. It is helpful to not do math in these initializations, but it's only initialized once, so it's not a big deal. But if you're very, very, very picky about performance, this is not as good because you can do the math yourself and have an answer. So now, because we changed the values a lot, the acceleration is going to accelerate a lot faster, and the stopping acceleration should be almost instant. And so we'll test, run our game here. You see we ramp up, and when we stop, we almost stop instantly. As you can see, it does take time to get to max speed, so it's a little bit floaty, and depending on your game, you might want or not want that. The floatiness makes the character feel heavy, and so if you have a very heavy character, you're going to want that time to max speed to be a little longer. For me, I'm going to reduce it to 0.5, which will result in this being 2. So now, if we run this again, it should accelerate a lot faster. And as you can see, we're moving a lot faster. It doesn't feel as slow and lethargic, but it does feel a little bit heavy because of the lerping. This is actually a trick that some VR games use to simulate the effect of heaviness when picking up an object. Because in VR, you're just holding a controller and it'll never weigh more than it does, and there's no way to make it suddenly weigh more. But if the object is lerped with a lower acceleration, it feels heavier, and so it can simulate that sensation, mostly on a psychological sense. And so you can use that to make the character themselves feel heavier or lighter if you make the acceleration very fast. Now, the stopping acceleration can be slower as well, but with the player, they're going to have less control over how they're moving. Because if they try to stop, and then the character takes 10 steps forwards, they might have fallen off a cliff. Of course, this will always, always, always have to be adapted to your game. And now the extra bonus is what we can do is move and slide returns a value. You can see it returns a vector 3 because what it's returning is the remaining velocity after physically moving the object. And so we should actually be setting velocity equal to that. That way, if the character impacts an object, it'll consume all of the velocity, the kinetic energy of the movement, and it'll return what's remaining, which would be 0 if the restitution is low enough. And so this way, instead of moving and then continuing to slide against the wall, once you hit something, it'll stop. And then lerping over to the next side will be a lot faster. We covered a lot. We also didn't cover a lot at all. Because of this episode, I had to get into Godot topics as well. The homework for this episode is going to be to try to make a sprint button. You should have everything you need to know in this episode. If you need external resources, go for it, but I believe you should be able to do it on your own, and that's what will be most helpful for you. I'll give you the hint is that you do need to go back into the input map to get it set up. If you can add sprinting all by yourself, you're well on your way to adding other fun movement features like crawling, jumping, and other dynamic movements that are more common in many first-person 3D character controllers in modern games. Now, as a closing, I want to say thank you all so much for watching. At this point, I'm very certain this is not the character controller that you want for your game. I'm sorry for that. Next episode, we're going to be adding mouse looking, which will mean that the player can look around the world as well as move in whatever direction they're facing instead of being restricted to the axes. This episode was a little longer than I expected it to be, and I already extracted that Basics of C# Theory episode out of this script to make this episode a little shorter and more digestible. Let me know what you think in the comments. Should I keep extracting these theory segments, or would you prefer to just have one big, massive episode that covers everything? Let me know down in the comments. Now, I want to thank my lovely patrons over on Ko-fi that helped make this possible. If you want to join them in pledging at least $1 a month, you can see these episodes as soon as they are finished, instead of on the weekly release schedule. These generous people are Noel and Miguel. Thank you so much for supporting me.